Okay, so we're going to move on and we're going to learn something that should be new for everybody, which is the idea of a radian. A radian is very similar to a degree. So in a circle, there are 360 degrees. So a degree is just the, amount of angle that is 1/360th of the full circle. That's probably too big, but general idea there. Now, there's a different unit system that are called radians. And the number of radians in a circle, radians are larger. There are a little bit more than 6 of them, but to be precise, there are 2 pi radians in a circle. So approximately, 6.28 radians in a circle. Now, let's talk about why we might want to use this number system over this one. Um, as a quick little comparison, this is very similar to describing the difference between like inches and meters, right? They're both measuring the same thing, but they're just two different lengths. They're two different units that are both measuring the same thing. So these are both measuring angles, but they're two different sized units, where radians are bigger. Now, first of all, before I want to talk about why we might use radians, I want to talk about why we use 360 degrees in the first place. So that is not like a number that we discovered out there somewhere. We didn't do some math problem and discover that there are 360 degrees in a circle, just like we didn't discover that there are 24 hours a day. These numbers, 24 and 360, 60 minutes in a hour, 60 seconds in a minute, all of these numbers, 360, 60, and 24, they were chosen for a particular reason. So let me try to illustrate that reason real quick. If I put any of those numbers, 360, 60, 24, if I put any of them and I divide them by x, so what that means is like I'm going to divide them into different sized pieces. So if I just divide by 1, obviously I get the same number I started with. If I divide in half, I can get half of 360. I can get half of an hour or half of a minute. I can get half of a day. So these numbers turn out to be whole number integers. I can get a third of a circle, so I can get a third of 360. I can get a third of an hour or of a minute. I can get a third of a day. I can get a quarter. I can get a fifth. Now, a fifth of a day is where we start to see our first decimal crop up, but we can get a sixth of any of these. We can't get a seventh. We can get an eighth for a couple of them. We can't get a ninth for most of them, but we can for a circle, and we can get a tenth for 2 out of 3 of these. So these are called highly divisible numbers. If we compare these, so instead of 360, let's say somebody said, okay, well, that's too many degrees. I don't want to count up 360. Let's just stop at 350. Well, if you did 350, then if somebody asked you for a third of a circle, you're suddenly having to report these numbers that don't really end, these irrational numbers that just keep going on forever. So you could go through, you could try out, multiple different numbers and find that that's going to be the case for all of them. You could have said like, well, what about a similar number but half as big? Well, it works out for all of these ones, but as soon as we get to an eighth, we're into decimals. We could have, let's see what happens if we go twice as big. Well, twice as big didn't fix any of these. So the one that I had that was already a decimal, it's still a decimal, and all the other ones are still integers. So 360 is what we call a highly divisible number. Okay, that's why we use it for the degrees in a circle, just like 24 is highly divisible. Okay, so if somebody said 24 hours, I don't want that long, I want 23 hours in a day. Well, that person's going to be having a hard time telling somebody what time it is after a third of the day has gone by or a fifth of the day has gone by. 24 is just a number with a lot of whole number, integer factors. So that's why we use those. So that's where we're starting from that 360. Now, what we are going to do instead of 360 degrees is we're going to start using pi with circles. Now, the reason why you'd want to use pi for a circle might not be clear as first. So like if you think about it this way, well, if I'm dividing by different amounts, I'm not going to get any whole numbers here. Well, that's only if you're trying to record it as a decimal. So if I go over to a drawing real quick, if I have a system where my degrees are in terms of these things I'm calling radians. So let's go to a circle real quick. Okay, so I'm saying that all the way around that circle is 2 pi radians. Okay, so radians, just like the word degree, is the unit, and this is how many of them go around the circle, 2 pi of them. Okay, now first of all, this is based off the idea that this circle that we're drawing right now has a radius of 1. So it has a circumference of 2 pi r, so 2 pi times 1. Its circumference is 2 pi, and the angles are going to be based off that as well. So what we have here is 2 pi radians. So if I went halfway around the circle, if I went 180 degrees, okay, if I had an angle that was 180 degrees, that would not be 2 pi radians, that would be pi radians. And if I went a quarter of the way around a circle, I would have pi over 2 radians. And if I went an eighth of the way around a circle, if I just went to right there, I would have pi over 4 radians. Okay, and if I, went half of that, I would have pi over 16 radians. So the basic idea here is that what's nice about using radians, one feature that's nice, is that anywhere along the circle should be able to be expressed as a ratio of whole numbers. So um, as long as we keep this pi as the symbol pi, right, as long as we don't write out 3.14, we should be able to specify any fraction of the circle. So if I wanted like, a 44th of the circle, well, it would just be 2 pi over 44, right? So that would be the amount of radians that would put you a 44th of the circle, whatever little slim amount that is. So it's just a different number system that kind of takes into account a value that we have that we already know is important to circles. And it kind of puts it all in terms of that value. And that's going to be what we're going to be working with for most of the time here. So again, 2 pi radians is equivalent to 360 degrees. Okay, so if we just had like a radians column and a degrees column, if I have 180 degrees, that should be pi radians. If I have 90 degrees, that should be pi over 2 radians. If I have 45 degrees, that should be pi over 4 radians. So thinking about like how much is a radian, well, to get that, we would just need to take 360 and divide it by 2 pi. So if I do that, 360 over 2 pi, let's see what we get. We get 57.29. So in terms of degrees, it's kind of a weird number, what a radian is. Okay, 57.29 degrees per radian. That's how many degrees are in a radian. So if you want to imagine, like on your little coordinate graph here, if you want to imagine what a single radian looks like, well, this would be like 45 degrees. This would be roughly 60. So this angle right here is just about approximately 1 radian. Okay. Now it doesn't matter that it's a weird number of degrees because we're just moving away from this system. Okay. In the same way that like if you compared like inches to meters, there's a lot of people around the world that would say that 12 inches is a very strange way, 12 inches, 1 foot. These are very, very strange measurements. Talking about an amount of meters or centimeters is much better because it's like a base 10 system, and our number system is base 10. So why shouldn't our measurement system be base 10? It's kind of a similar comparison. So if somebody was to say, like, how many inches are in a meter? So let's see this, inches in a meter. So if you were to do this conversion, and you get, okay, 39.37. Well, that's a weird number. Well, the response to this would be like, it doesn't matter that this is a weird number of inches, because we should just stop using inches. We should start using meters because it's just a better number system for what we're trying to accomplish. In the same way, radians is just a better measurement system for dealing with circles. It deals with ideas that are like actually intrinsic to the circle itself, rather than just some kind of arbitrary number that we picked out because it divides well. Okay, so let's hop into the actual book and kind of walk through those ideas in the way that they summarize them. So angles can also be measured in units called radians, which are based on arc length. A radian is the measure of an angle in standard position with a terminal side that intercepts an arc with the same length as the radius of the circle. Okay, well, let's draw that out real quick because that's a lot of words right there. So what they just said there is that what a radian will be is the angle where this length, this radius here, is the same length as this arc. Okay, so if we have 2 pi of these radians, right? If we have a little bit, over 6 of them or so, 1, 2, 3, 4. I didn't divide that up very well. Anyways, that is their definition of a radian. It's the particular angle. Okay, so I'll call that 1 radian. Is the particular angle that gives you the same length for the radius as it gives you for the arc length. That's just a different way of describing it. The circumference of a circle is 2 pi r, and an angle that measures 1 radian has an arc length of r. So 1 complete revolution around the circle equals 2 pi radians. Okay, that should make sense. So your circumference is 2 pi of these. Okay, so it's 2 pi, it's about 6 of these things to get around the side, 2 pi r, and therefore the full measurement around the inside should be 2 pi radians, right? You do about 6 of these angles to get around. Once again, I think I drew that a little too big to make it work out, but that's the main idea. So degrees to radians, if we're trying to convert a degree measure to radians, multiply the number by pi radians over 180. If you've never taken like a chemistry class or something where you're doing what we call dimensional analysis, this might not be super intuitive, but what you want to do is you want to look at the units. So if you have a number of degrees and you want to get to a number of radians, you're given degrees, you want to get to radians. Well, then you need to multiply by some sort of ratio where degrees is on the bottom, so that these will cancel out on top and bottom, and that radians is on the top. Okay, so we know that 360 degrees is 2 pi radians, but they're just cutting both those numbers in half. They're saying the conversion that they would suggest you use is pi over 180. Okay, so if you have, for example, 360 degrees, just put a symbol like that, you would multiply by pi over 180 in order to get that you have 2 pi radians. All right, 360 over 180 will give you your 2. The degrees will cancel out on the top and bottom, and you'll be left with just the radians. Okay, so that's how you would get from degrees to radians. If you're going the opposite direction, then you just flip the fraction over so that you're canceling out radians and you're introducing the degree symbol. Okay, So it says there are special angles with equivalent degree and radian measures that may be helpful to memorize. Other special angles are multiples of these angles. So there are 30 degrees, 60 degrees, 45 degrees, and 90 degrees. All four of these turn out to be very kind of simple fractions to remember. Now, 30 and 60, if you haven't seen geometry for a little while to know this, 30 and 60 are kind of important because they are what you get when you split an equilateral triangle in half. So if you have an equilateral triangle where all three angles are the same and all three side lengths are the same, when you cut that thing in half, you end up with 30, 60, 90. So this is, we call this a special right triangle, the 30, 60, 90 triangle. And three parts of that are in here. Three of the equivalent radian amounts are in here. So it's we'll see later that these are important ones to keep in mind. They're just kind of good reference points around our circle. Finally, a central angle of a circle has a vertex at the center of the circle and sides that are radii. Okay, a central angle of a circle has vertex at the center of the circle and sides that are radii. Okay, that's fine. So they're just describing sides that are radii positioned on the center. Okay, basically what any kind of angle within a circle, how you would imagine drawing it. The endpoints of the intercepted arc lie on the rays of the central angle. These side by side. Okay, there we go. The endpoints of the intercepted arc. Okay, the intercepted arc, the endpoints of it lie on the rays of the central angle. Yes, they do. They are at the end of those rays. If you know the measure of a central angle and the radius of the circle, you can find the length of the arc that is intercepted by the angle. Okay, so they're saying if we know this angle and we know the radius of the circle, we should be able to figure out what this arc length is. So for a circle where that radius was 1, the angle and the arc length were identical. For any other circle, it's just going to be a multiple of the radius. So if that radius is 2, right, if this is a radius of 2, and this angle is like, I don't know, let's do a different thing. Let's do a 90-degree angle. So this would be, trying to think about our radians, we have 2 pi all the way around. We have pi halfway around, so this would be like pi over 2. Okay, pi over 2. Now they are saying that in order to get this arc length here, all we have to do is multiply these two values together. Therefore, our arc length should be pi. Okay, well, let's try to verify that. The circumference of a circle is 2 pi r. The radius in this particular circle is 2, so the circumference of this circle should be 4 pi. And this is a fourth of my circumference, so it's just 1 pi. Okay, looks good to me. So that is the concept of an arc length. To get this length, which they're calling S here, you just multiply your central angle by your radius. And I believe that is all that we need to go over before we can start looking at some examples. Yes, it is. Okay, so we will move on to example number 4 in the next video.